Okay, so here we're just going to talk about the methodology again. So this is stuff that was taken from the last week's lecture. So the concept is that we have internal member forces are assumed to always act in a direction of the member. If a resultant force acts away from the joint, the member is said to be in tension, and if the force acts into the joint, the member is said to be in compression. So what we're saying there, so we've got some kind of framework. It's going to go red on me. No, there we go. There's my framework. Oh no. Need to bring my pen across. And I will put a hinge here, and a pivot here, and we'll load it up with a weight. Okay, so we're a weight, I think, of 20. I think it's 20 kilonewtons. So, right. So what we're saying here. So we've got these hinges. We've got the supports. We've got a weight. Weights obviously have to go at the joints. Hinges and supports, they all have to be at the joints. So in between each joint there is something which we call a member, and in that member we are saying there can be a force, just like there can be a tension inside string. So all those forces have to cancel out. So if there's a force here, what we can do is we can say that I can see what that force is, and I'm going to say that that the internal force is assumed to always be in the direction of the member. What I mean by that is I assume that the force is always going to be away from the joint. So I assume there's going to be a force away from the joint, a force away from the joint. Now those two forces, which are in the same member, they have the same value. So let's say, for sake of argument, we work them out to be -10. So we work out what this force here to be -10. It's not going to be, by the way, but the force then can point in this direction is also -10. So I've got a -10 pointing in this direction, and I've got a -10 pointing in this direction. Okay, so two -10s point in opposite directions, so they cancel one another out. Okay. Now if it turns out that the forces are into the joint, so if the forces were pointing this way, then the beam, then the member, sorry, is going to be in compression. So how does that work? Let's go back to just imagine we've just got a single strut. So I've got a single strut there, and I'm going to apply some external forces to it. So there's my external force, which I'll call 10 newtons, and then I'll apply another 10 newtons here to stop the body flying off. Okay. Now I assume that there's going to be some forces inside. So there's going to be an internal force inside and an internal force inside here. So these two internal forces will cancel each other out, so nothing's changed. But now this is what the method of joints does. That's a clever bit. Is we take a nice colour like this and we cut around a joint. Okay, so I then take this away and say, well, I've got a external force here, 10 newtons, and I've got this internal force which I need to work out. So I'll call this is going to be my joint A, and this is going to be my joint B. So I call this force, call it AB. Well, if 10's going upwards, let's resolve the forces going in the upwards direction. So we're going to have 10 plus AB equals 0. So AB equals -10. Right, so the force needs to be in the opposite direction, so therefore it's in compression. Okay, and this force here, if I then take a cut around the other one, so cut around the joint B, I'm going to get the same thing going on. So I'm going to get 10 newtons going downwards. I'm going to have my force, call it AB again, and it's going downwards. If I resolve the forces downwards this time, I would get 10 going downwards plus AB going downwards equals 0, and then again I get AB equals minus 10. So it doesn't matter which joint I choose, I end up with the same result. AB equals minus 10 for this strut. Okay. Oh dear, didn't think about that. So that was my my notation there. So you can see it now. Sorry. So we got the 10 plus AB equals 0. AB minus 10 is now in compression. So notice I put a C there to tell you that it's in compression. Okay. Sorry about that. Let's go back down. Okay, next, method of joints. Assume that all the internal forces are tensile, pulling away from the joint. A negative answer indicates the direction of the force is incorrect and that the member is therefore subject in compression. So we've seen that with the previous problem. So we will have our strut here. We're going to apply some external forces. So I'm applying a force here. I'm applying a force here, and I'm going to assume that the internal forces are tensile, i.e. pulling away from the joint. So they are my red forces. So I've got an internal force here pulling away, an internal force pulling away. Okay. Now, if you imagine the string problem, so we've got a thick bit of string this time. So with the string, we're going to have a weight at the bottom, and we're going to have to hook the string around a hook at the top, which means we'll have a reaction pulling it upwards. Okay, so the internal force in this case is away, external force is away. Now can you see when you take the method of joint, cut around here, for this case, which is a compression case, we're in compression, you can see that the external force and the internal force are both going off in the same direction. So when we pull this away and add up our forces, the red force needs to switch around its direction. It will need to be a negative answer for this force and this force to cancel out. Okay, so that will tell us that that's a bar, a member in compression. Here, however, with the string problem, the force is going away from the weight and it's pointing in this direction. So in this particular case, my bar is going to be, my member is going to be in tension. So that's in tension. Is that making sense? The values that you get, so whether they're positive or negative, you need to keep them positive and negative as you move around your joints and solve the various joints. So for method of joints, determine the unknown external forces on your free-bodied structure if you're required to do so. Sometimes exam problems, for example, will already solve them for you, so you're only looking for the internal forces. So sometimes it might already be done. Start at a joint where there are only two forces that are unknown, which will be meaning that you're probably going to be looking for a joint where there's only two members. you're looking for some sort of joint which only has two members usually. Assume that each member is in tension, so we draw little arrows pointing away from each joint, and we're assuming that's our definition of tension. Resolve any angles in the x and y components, as if we need to. We might be able to skip this step and apply two equilibrium equations in the x and the y directions. So that's the next stage, where we're going to resolve forces either in the x direction or the y direction. Now, which one you do first sometimes depends on the problem. So if you've got a member, if we're doing our triangle problem, for example, and this is going to be the joint I'm interested in, the one to do first in this case is resolve the forces in the y direction. Why would you want to do that? Well, when you cut the members, these are your unknown forces. So you've got a force going off in this direction, you've got a force going off in this direction. If you resolve the forces just going in the y direction, the only unknown that you pick up is this force going off vaguely in the y direction. If you resolve your forces first going in the x direction, then there you've got a little bit of this going in the x direction and all of this going in the x direction. So with method of joints, sometimes it's best to decide, make a decision which way round you want to resolve your forces. It won't make any difference at the end of the day, okay? It just means that the maths looks a bit nicer and a bit easier to do. Work around the structure to determine the internal forces as required. Okay, so that's your final stage. So let's consider a problem where we are going to have a triangle. We're going to put it on a hinge. I'm putting my 20 kilonewtons here. That was what, 30 degrees. So this can be, I want this to be nice. What would be a nice isosceles, wouldn't it? So we got 30 degrees here with a pivot. 60. So that's quite a wide angle triangle here. So this one here is going to be an angle of 120. Right. So it's going to look far more like this. In reality. Okay, so quite flat sort of triangle. So 20 newtons, 20 kilonewtons are coming down. Now, what kind of tension are you expecting to occur in this member, and what type for a start? Well, those of you that are quite used to doing the string problems, well, you're probably going to be thinking, well, and seeing what I've been saying with struts and stuff, that this is a bit like maybe having two bars with 10 kilonewtons here and 10 kilonewtons here. My reactions at the bottom are going to both be 10 kilonewtons apiece. So imagine that, and then I'm just going to make my bars a bit sort of like so that they move out further and further apart. Okay, so we know if we had those two bars close together, like two legs standing up, that the force that we'd expect, the tension inside those members, just to be 10 kilonewtons. But what happens if we start spraying them out at angles? Do you recall what happens if you start doing strings and you have string problems and you're trying to make the angle so that you're trying to pull up the weight so that your string is trying to go horizontal? Can you recall what happens there, the tension in the string? What do you think will happen? Let's work it out and doing the method of joints. So the first thing we're going to do is we're going to take a cut around here. Well, the first thing we need to do is work out what the reactions are. Now, this is a symmetric problem. I'm not going to take you through that. You can work it out formally if you want to, but it's fairly obvious that we're going to have RAX equals 0 going in this direction. We're going to have RAY is 10 kilonewtons going in this direction, and for this thing here it's going to be I'll call this B, I suppose. This will be my check on my other diagram. C. Actually, sorry, no, that is going to be B. So my B is that. My C is here. And my A is at the top. Okay, so we've got B, A, C, like that. So RBX is 0, RBY is 10, RCY is also going to be 10 kilonewtons. Okay, so we're going to take the cuts around this B joint and examine this further. Okay, so when we take that cut, that will expose the internal forces inside. So that will expose this force BC going in this direction, and we put the lower letter in the alphabet first, the AB in this direction, and we've got this external force of 10 kilonewtons in that direction, and that's doing the method of joints to the problem, to that first joint. Okay, so I've got two unknowns. I know this angle here is 30 degrees, and I want to find, for example, what AB is. Now I know that if I brought those two reaction things together, that would end up as 10 kilonewtons down the member. But if I spray them out like that, what's going to happen then? That's the question. So we've got the maths worked out here. So we are only interested in this AB force here. So the AB force is going to be AB cos 60, because this is 30 degrees. So I need I can resolve this around because I like using causes. So I work out what the complementary angle is. So that's 60 degrees. So I've got AB times by cos 60, and then the force is going down. Okay, so in my case I've got this wrong, so the force needs to be going upwards. So I need to correct my working out here. So my force is going upwards, which means if I'm going to resolve forces going in the upwards direction, this needs to become a positive, so that's plus. Okay, and then the next one. Do a little bit of quick editing. So if this is going to be B plus, when I take it over to the right hand side, that will become minus, this will become minus, and this will become minus. Okay, so minus to the plus 10 goes over to the right hand side, that will become a minus 10. Then we divide through by the cos 60. Cos 60, try it in your calculator, equals half. So minus 10 ends up as a minus 20 kilonewtons. Okay, so the compression inside the bar, this AB bar, is going to be a value of, AB will be a value of minus 20 kilonewtons. Let's draw out our result then. So we've got 20 kilonewtons coming down. I've got an external reaction force here of 10 kilonewtons, another external reaction here of 10 kilonewtons, and I've worked out that the internal force down one of these beams, so I get the same answer if I do it on this side via symmetry. So I work out that this internal force here is going to be minus 20. And it's been balanced with another internal force here of minus 20. That's curious. So the internal force going down the bar is actually equal to the force that we're loading the bar with. If I sprayed out my triangle even further, I would get internal forces greater than the loading. That seems really weird. So the forces inside the members can actually be bigger than the loading itself. So the loading is not a limit for how much compression or tension that's going to be transmitted down a member. I'm supposed to be surprised. There you go. Please send me to drawing school. Right. But in this case, it's even quite surprising the fact that it's actually managed to reach the same value as the applied load, because we're going to have 20 being compressed down this bar and 20 being compressed down by this bar. So even that's sort of a surprising result. So, frameworks. This is really quite important stuff, and it's quite fundamental for your knowledge for your next 3 years. So don't think that you can skip it, because I'm afraid you can't. It's going to come back and bite you in the bum if you do. It's fairly important to follow the rules and get used to them for method of joints, and for the one that we're going to be doing this week during the lecture, method of sections, and try and learn them competently. My thing is just moved across. I don't know what to do now. Doesn't matter. There we go. Try to learn them competently. Very important to keep your signs the same as you move around the joints, because you need to keep track of whether it's plus or negative. So if it's a negative, you don't want to throw that value away. Very important to try and write stuff out neatly, because it will help you try to find mistakes for when you apply the method of joints in an exam situation. Okay, good luck.